So welcome to our second session. So our first speaker is Sergey Dolgov, who was at Moscow Institute of Physics, then Leipzig, then Max Planck, and is now an EPSRC fellow and lecturer at Bath. So Sergey has a very interesting EPSRC page where he points out that there are certain calculations that you would like to do which would take more than the lifetime of the universe to complete. So that's what I call the slow simulator. And his argument, I think, in there is that we can do things rather faster. And looking at the title, I suspect that these things will income.
Yeah, thanks a lot for the kind introduction. And thanks to all the speakers who gave talks on order decompositions before. So, I think you should be more or less well prepared. So what high-dimensional problems we have if you work with stochastic partial differential equations, and well, what approaches we have connected to the separation of variables. So this is a joint work with Scheichl in Bath. And yeah, so what we wanted to do, we wanted to merge some linear algebra and Lorentz decompositions and all the knowledge we have about uncertain problems. So the uncertainty quantification is general, well, it was told multiple times, I guess. So it occurs if we have some classical model, for example, but a model which features unknown coefficients or coefficients which are intrinsically random fields or something else. Like, for example, this very famous problem, which was even called the fruit fly, because all numerical analysts working on this kind of problem start with this one. So just the diffusion equation with diffusion coefficient parameterized with some random event in general. But of course, we don't want abstract events. We want to introduce some deterministic set of parameters using the Carhunian-Löw expansion, and maybe we can actually start with some finite set of parameters. And in the end, I don't have a stochastic problem anymore. I have a deterministic problem, in fact. But this deterministic problem is very high dimensional. So if I try to do what I would do with normal multidimensional differential equations to introduce reasonably uniform grid in all variables, then I can't just do this, because then the number of total degrees of freedom would grow exponentially in the dimension. And this dimension here can be between tens and hundreds or maybe thousands. It really depends on the accuracy of this randomness parameterization. So, but the motivation why we approach these problems at all, because often we have a low dimensional output of interest. We have this very complicated high-dimensional problem, but this is just to compute the solution which we never observe, because it's some high-dimensional function, or it can actually be considered as a random field if we let our fit parameters to be random quantities, not deterministic parameters. So what we actually observe, or what we can measure, is some quantity of interest, such as an integral or point evaluation, anyhow, but this is low-dimensional. And yeah, I mean, what we can think about, we can compute moments, then we can compute something like probabilities of events, that some quantity is smaller than some threshold, or vice versa. And we can probably think about quantiles, something else. But in between, we have this high-dimensional object, and the idea is to approximate it with a low-dimensional representation. So we have some low-dimensional input, just d parameters. And we have some low-dimensional output. And our hope is that we can possibly introduce some low-dimensional representation in between, to just be able to simulate it at all. And what I will use in my talk actually is based on the separation of variables and tensor products. So the idea is, if you have a function of many variables, you would like to approximate it by a sum of products of univariate factors. As you have seen in the talk by Lars, this is something very basic about separation of variables we can start with. It's just a sum. But in general, what we might have some complicated structure of this summation here. But first, I can just look at this and try to think why it's good at all. Because if we only store the right-hand side, and never the left-hand side, then we can store these factors here with the cost linear in the dimension, the univariate grid size. We can also integrate it with the same cost, because we can just compute one-dimensional integrals. The same for the point evaluations. But the main part of my talk will be actually on something more difficult because, well, it's fine if you can store the solution, but remember that the solution is given by this high-dimensional PD. So my concern for today will be actually to how to solve an equation efficiently. It's just a simple linear equation, like a diffusion equation, but it's high-dimensional, so we need to do something about this. And here, if we do it naively, we would have something completely enormous, like n to the power of 2d. Oh. Even if we use sparsity, we'll be here at this point. Anyway, what we can hope for if we use the Laurent decompositions, we can hope for some feasible complexity which grows linearly in the dimension, the number of variables. And of course, we have also seen some different methods. Basically, there are more or less 3 families of the methods. First of all, we can just use random or quasi-random sampling, and this is a very general approach, easy to parallelize. Sometimes you can prove very nice theorems even, but usually you would have reasonably slow convergence of your accuracy with respect to your complexity. Then you can use some more structured representations. For example, you can approximate your solution or your coefficients in the basis of polynomials of bounded degree. And again, you can also interpolate it on the roots of these multivariate polynomials, so you can possibly have some efficient solution procedure. And the storage complexity would be somewhere in between. It usually converges faster than Monte Carlo, but probably not as fast as we could have. And why I put plus in my research here, because in generally what might happen is, so what Laurent decompositions are eventually related on is some linear algebra operations on discrete level, something like the singular value decomposition, some optimal discrete operations. And this means that they can potentially leverage any basis we can cook up for our class of solutions. So if we can prove a theorem that the solution is well represented in the polynomial basis, fine. Each polynomial is a tensor product function. So we just sum them up all together, and we immediately get a bound on this number of terms here. But what if our solution is not well representable by polynomials, but it's well representable by trigonometric polynomials? Or what if it's well representable by, I don't know, rational functions, a tensor product rational functions? Here we would need to derive an explicit ansatz. In the explicit basis, we would think it's good, but if it's not good, well, again, start everything from scratch. Here we can potentially use whatever optimal basis our solution might belong to. But the problem, of course, not just the representation capacity. The problem is, of course, also what's the computational complexity. Because if you have some good representation capacity, but actually computing this representation takes exponential amount of time, that's of no use. So the idea of my talk today will be to show you that actually for the stochastic collocation of the stochastic partial differential equations, we can also have a good algorithmic complexity of these low-rank representations. It's very important fact because if you consider some complicated examples, or maybe you can actually consider some simple examples and then try some, let's say, straightforward approach with these techniques, you might quite often have a reversed picture. You might quite often have sparse grids performing better, or even quasi-Monte Carlo performing better. So in order to really leverage this potentially optimal complexity, you really need to develop new algorithms. And this is what I will talk about. So generally, yeah, if you can remember what our goals, of course, we want to store the solution, but then we also want to solve equations, and how we do this in general in high dimension, and how we can use the sparsity of the matrix which we might potentially have. And if we stick to the tensor product decompositions, there are basically 2 concepts. So one concept is an iteration. So most of the computational algorithms are iterative algorithms, but this iteration goes in a very specific way. It goes iterating over the factors of our decomposition. So this is what's called an alternative iteration, which stems from the term alternating least squares, which was used something like half a century ago, I think, for the data analysis in these separated forms. But there is more to that, because if we really want, well, first of all, if you really want to compute a high-dimensional function, if you want to approximate it in this representation, but also if you want to solve a particular equation with a particular structure we have in our stochastic PDE, we might need something else. We might need some interpolation ideas. And this is what I will show you today. But the good thing is that in order to describe these algorithms here, we don't even need to go to high dimensions. We can actually start with 2 dimensions where everything is very simple. So in 2 dimensions, yeah, as we have seen, what we can say that we have a function of 2 variables, and we just discretize it on a tensor product grid and collect the values into a matrix. And what we can try to do, we can try to approximate this potentially large matrix by a low-rank matrix, right? And then only store the low-rank factors of that matrix. And then, of course, if the rank here is much smaller than the original matrix size, we might have potentially a very good reduction in storage. And we can also use the single value decomposition, which is proven to have the optimal rank versus approximation accuracy dependence. So the best low rank approximation we can achieve can be actually delivered if we are able to access the whole matrix. And this is a very dangerous assumption, because in reality we of course can never access the whole matrix because it's large. If we can access it, we can just integrate it directly to obtain our quantity of interest, whatever. So it's really not possible to start from full matrices, right? So what we want to do instead, we want to build a low-rank approximation using much fewer number of evaluations from our function or from our matrix, whatever. Sometimes we can have some analytical expansions. For example, we can have our Carhunian-Löw expansion in the stochastic PDE, which is linear. It is just an affine expansion, and it's not difficult to see that it can be written in a tensor product decomposition exactly. But otherwise, if you don't have this nice situation, what shall we do? So this is where we need a class of algorithms which is called cross algorithms. So generally, this is the family of sampling algorithms, but a sampling of very particular kind. And the idea, as I said, is to reconstruct a low-rank decomposition using only a few evaluations. So again, if you look for matrices, what we can observe, okay, so we know the SVD. It does the minimization of our true error. And if you remember some classical interpolation and some classical polynomial approximation, you can remember that, okay, probably minimizing the error is not always efficient. What we can try to do instead, we can try to just interpolate. And this is what we can do with the low-rank decompositions as well. So I can say that, okay, my low-rank decomposition is exact, but only on a finite subset of entries. So let's assume we are given 2 sets, I and j, from our original set of indices, but of smaller cardinality, of course, otherwise it's of no use. And then we pose these 2 equations. So if we solve them, I'll show you how does it mean. This means that we have this approximation formula here, which is also a low-rank approximation, but now it has these very specific factors coming from the original matrix entries, not the singular factors or something more complicated. That's why it's called the cross decomposition, because we really select a cross of entries from a matrix and build our approximations from them. Yeah, so here is the formula. This looks very easy, but of course, the crucial question about all this is, what are these index sets, right? I mean, I could think of any index sets, but will they give any good approximation? Who knows? So what are the best index sets for the given rank? And can we actually compute this index set? So can we at least approximate them somehow? And then the question in the last part of the talk would be, of course, what to do with more than 2 dimensions, because we can gain some understanding in the simple scenario, but in the end, we need to solve this complicated high-dimensional PDE. So the answer to the first question is reasonably known. In order to achieve the best index sets, we just need to look through all possible R by R submatrices in the original matrix, and then compute the determinants, and the absolute determinants to be precise, and then take whatever index sets which deliver the maximal modulus of the determinant of these submatrices. If you do this, then we have reasonably nice estimate that the maximum norm of our error is just by a factor of rank plus 1 worse than the single value decomposition error, which is good, except that it's never possible in practice, because in order to look through all possible submatrices, we need to explore an exponential number of them. And this is why most of tensor algorithms are iterative. That's why we need to go into heuristic algorithms in all numerical practice. But this is what we can do. So we assume that we are not given the original matrix fully. We assume that we can't do the volume maximization, but we can assume that we are given some of the index sets. Just any set we can cook up. Maybe just random if you have no better knowledge. If you have some knowledge, well, maybe it's there. And then we just sample these R columns of the matrix. It's feasible, of course. And then we want to run some algorithm of determine optimal indices in this long thin matrix. Because it's a long thin matrix, this is doable. So to find an R by R submatrix in an N by R matrix is not NP hat anymore. It's actually of complexity N times R squared. So this is doable. And these indices should, of course, be better, because now we have run some optimization algorithm on the actual matrix elements. So these indices are definitely not worse than our initial guess. And then we can repeat. So this is the idea behind the alternating iteration, that we really iterate between the factors of our representation. Or if we speak about these interpolation cross algorithms, we iterate between the index sets on the left factor and on the right factor. And if this algorithm here, which can be just, by the way, this can be just a row pivoted LU decomposition, which will already give us a good enough set of indices. But then we can do something better. We can actually find a matrix which maximizes our modulus of the determinant, because again, this matrix is thin. So we can actually run this, and of course, in each step, this modulus of the determinant never gets smaller; it can only get larger. So this method converges, and in most important cases in practice, it converges to very good sets, which are very close and give the approximation which is very close to the true maximum volume approximation. And then we need the number of evaluations from the matrix which is linear in the size and linear in the rank, which is also good. And then remember that this interpolation formula is not really what we want to store, because it has these three factors. So it has these two factors and then another factor in between. In order to store the Lorentz decomposition, we just need two factors. It's not a big deal. We can just group some of the matrices together. For example, we can group the first factor with the small matrix in between together. We can group the small matrix with the second factor and call this our representation. And this is actually a good thing to do, especially if we need to solve the stochastic PDE, as we will see later. Because if we have this factor here, if we store this factor, if we now evaluate it at our index set, if I just plug this J here, you see that these two terms cancel. So we have this important property here. And now if we apply this algorithm to a matrix constructed from a discretized function, we would see that this factor looks something like Lagrange polynomials. So it has ones at our selected pivots and, well, some interpolating entries otherwise. And as we'll see, this will be very important. Also to solve an equation, not just to interpolate. From the interpolation point of view, it's also good because you see that the norm of this object is bounded. So this algorithm is also numerically more stable than just leaving this three-term formula as it is. So then, of course, we can do even better. If we want to have even better numerical stability, what we can do, we can compute the orthogonalization of the factors before doing this inversion. And this is generally better. And if you want to adapt the ranks, then it's easy enough to just expand our factors by few other entries. So if we have a rank R, we evaluate not R columns from the matrix by, let's say, R plus 1 or R plus 2, whatever. We take few more columns. And then, of course, when we then run the pivoting algorithm, it will give us not R pivots, but R plus 2 or whatever. So we can increase the pivoting sets, and doing this procedure, it can increase the rank. And if we started with a low rank initial guess, we can adapt it until our required accuracy is met. And of course, there are different algorithms because this idea of iterating across factors. So why I choose it in particular? Because it's easy to it will be easy to generalize to high dimensions. But if we speak about matrices, there are actually other algorithms, and some of them are more efficient. Some of them have theoretical guarantees. We can use the adaptive cross approximation, for example, which adds rank 1 components, so which builds up an approximation by adding rank 1 components. Or we can use empirical interpolation methods. There we need to start with the full matrix. But the gain of that is we have a theoretical guarantee that if we start from the singular vectors, we can actually find our optimal pivots. But in high dimensions, as I said, it's more convenient, and sometimes the only way to do is to run this heuristic but efficient alternative iteration. And now let's get back to solving an equation. Because this is all fine if you have this interpolation algorithm. For example, we can apply it for constructing a coefficient of our equation, right? So if it's not just an affine expansion, if it's something more complicated like the log normal coefficient, which is an exponent of an affine expansion, it doesn't have a closed form expression in the low rank way, but we can use this interpolation algorithm. But if you now really want to compute the solution, so you can construct finite element discretization in space in our gradients, but in our extra parameters, which stem from the random quantities, I really want to do just the collocation. And because if I do just the collocation, then what I get in the end is a block diagonal matrix. So each block here corresponds to this spatial discretization, to this weak form here. But with respect to different grid points in stochastic parameters, we just have a set of independent systems. And this is very helpful. You might notice that we are actually solving the whole solution. So as Lars pointed, we can have different ways here. We can look for the quantity of interest directly. And usually, a quantity of interest should have fewer degrees of freedom than the entire solution. But because of this block diagonality, I actually want to work with the entire solution. And it might actually be more efficient then. So we have this matrix, a block diagonal matrix. Every block is not diagonal. So we need to do something for this. And we know that we can use the cross algorithms if our function is defined pointwise. If you can evaluate every entry of our function or matrix without accessing other entries. So we are just given a set of indices. We are getting one entry. If you have a system of linear equations, it's not the case anymore, because all entries of the solution are coupled through the matrix, right? So what can we do here? Is it not applicable at all? Or can we actually do something? So let's have a look. Let us rewrite our interpolation equation, first of all. So we have seen that our equation was that our low rank expansion was exactly equal to our exact function at the subset of points. So let's mimic it by multiplying it with some submatrix of the identity matrix. So let's construct this submatrix, which exactly evaluates one of the factors on the pivoting set. Yeah, so just this way. So we have this equation, and I can just insert a dummy identity matrix there, because it doesn't change the equation at all. Yeah. But now I can think, okay, so if I am constructing a Laurent representation of a function directly, and now I want to construct a Laurent representation of the solution. So if I construct in a direct approximation, then we have this equation with the identity. But if we have a system of equations, well, why? I can replace this identity by my matrix, right? Here it is. And just plug in the matrix in. And now let's see what happens here. So this is, I'll let this as it is. And this is my exact right-hand side, because this is my exact solution. This is the right-hand side. And now I have all my objects here. So I have the matrix, I have these pivot sets, and therefore I have this projection matrix, and the right-hand side I have as well. So this is my equation. This is my equation on the elements of these Laurent factors, if I have a system of equations. Of course, it's a still question if it does any better for the stochastic PDE in hand. So let's see how it's constructed, first of all. We have always assumed that the coefficient is given in a Laurent expansion, because if the coefficient cannot be even approximated in a form like this, there is no way we can do. But if we assume that this actually holds, then it's not difficult to see that the matrix can be represented in a similar form. If you use a finite element approximation in space and the collocation approximation in the parameters, we see that the matrix can have this Kronecker product form, where the first factor is related to our finite element basis in space, but the second factor is just a diagonal matrix, or there is a set of diagonal matrices actually, with this D being the collocated factors in the parameters. And that's good. So we have this diagonal matrix. Hold on this. And now we remember that our cross algorithm has this property here, that given the factor evaluated at its optimal indices is the identity. So now we plug this guy in. We take this projection matrix, which acts as this. So it takes j rows of the D matrix. And now they are multiplied by this factor. And after little calculations, you might see that actually this product here exactly exploits this identity. So in the end, what you have is just a small diagonal matrix. So you have the same factor from your finite element basis in space. Kronecker product is small diagonal matrix. And this is the equation on the elements of your other factor. So this is it. This is the equation, because what does it mean is that if you run our cross algorithm, we draw some optimal pivot from our second factor, which is given from the initial guess, for example. And then we just need to solve few independent deterministic PDEs at these indices here. Because these indices you will map to the values of your parameters through your discretization grid, through your tensor product discretization grid. And therefore, you just need to solve this independent set of deterministic equations, just the same way as we do in the Monte Carlo approach, a stochastic collocation approach. And we can easily parallelize them. We can use optimal preconditioners for each of these equations, or maybe even closed source software, who knows. So this is easy to do. It would be difficult if we had these matrices coupled, as might be the case if you also use Galerkin projection in the parameters. And then we go back. So we know that each block is not diagonal anymore, but it's fine. At this point, we can just use the standard ideas from reduced basis. I can just use the Galerkin projection, because we have computed an optimal factor. So we have optimized the first factor here. And now we use the alternate iteration. So we can make an orthogonal matrix out of this factor and construct a projection matrix and solve this Galerkin system for the second factor, which accounts for our degrees of freedom in the parameters. And this projected matrix is again diagonal, but now the diagonal is larger, it accounts for our grid sizes. But still, we solve M systems of size rank by rank, which are small, so you can just use the Gaussian elimination, never think of anything more complicated. Yeah, so this is almost the same as in the reduced basis if we just stay in 2 dimension. The only difference is that in the reduced basis, we build the basis first, then solve the reduced problem and full stop. Here we can use this alternative iteration of moving back and forth. So if our initial guess was very inaccurate, we can do 1 iteration. It might be still very inaccurate, but then we can iterate back and do a few iterations like such. And in some problems, it might need just 1 iteration. I think what Anthony might also talk about is that sometimes using these cross approximation algorithms, it's enough to carry out just 1 iteration, start with some random samples and do 1 iteration. But if you have a more complicated solution, we can do more, but usually again it's of the order of 10. And this approach is also extensible to many dimensions in quite a straightforward way. So now if we have d variables, what can we do? Yeah. So we use the approach which, I don't know if you've seen it so far, but which was definitely mentioned in passing at least. The so-called Tensor Train decomposition, or the matrix product state decomposition. And this is also a particular case of the hierarchical tensor decomposition introduced by Lars. So what we can do is we can use the Lorentz decomposition of matrices in high dimensions. And we can start with a particular simple way of doing this by just writing a linear formula. There's just a linear product of univariate factors with these summation indices. And with the particular structure, the summation indices where each extra index enters only 2 neighboring blocks. It's particularly easy to operate with because then each factor there is at most a 3-dimensional array. So we can store it in the memory, that's easy. And now instead of the single rank of a matrix, we have these TT ranks, but they're actually the matrix ranks of the corresponding reshapes of the original tensor. And then if these ranks are small, then we have the storage, which is again linear in the dimension, linear in the univariate grid size. Now it's quadratic in the rank, but well, we can live with this. And how now we deal with the stochastic PDE? So we assume now that we are given a tensor train representation of the coefficient. Again, if we have a Carhunian-Löw expansion, for example, we can just write it analytically, because it will be just a sum of univariate factors anyway. If you have something more complicated, like the log normal case, well, yes, then we need to run an approximation algorithm, maybe the cross approximation algorithm. Or we might probably do the Taylor series if the variance is not too big. Anyway, we need to compute the coefficient somehow. And then we can immediately write the matrix, because again, due to the linearity of both our equation and our representation, we can distribute some operations and get the matrix rising from our finite element space in the physical domain, and then the product of diagonal matrices corresponding to discretized factors in our stochastic variables. And this, so this matrix is again block diagonal, yeah, because of these diagonals here, but it's also it also has this product structure, and that's why we can generalize our hybrid algorithm, which does the Galerkin projection on one hand for the special degrees of freedom, but the cross interpolation on the other hand for the parameters. So here how it goes. So first of all, we have this alternative iteration which goes over each factor. So it starts from the first factor, do some calculations, goes to the second factor, do some calculations, and so on and so forth. And then it goes back and forth. And the algorithm on a high level can be written just in 4 lines. So we start with some initial guess, of course. And for example, we can just start from the coefficient, especially if you have a log normal scenario. Then the coefficient is the exponential of something, And the solution is roughly proportional to the exponential of minus that sampling. Not exactly, of course, but qualitatively, we can think that it would be a good initial guess for deriving these pivoting indices, or pivoting samples in particular. And so this is what we do with the right, with all the TT blocks on the right of our current stage. And with all the blocks on the left of our current stage, we construct just the Galerkin projection matrix. And then we construct this hybrid matrix here, solve it for the elements of the chosen block, and then go back and forth along this decomposition. And this hybrid matrix is the most important thing. So this is where the most computation, where the actual computations of the scheme sit. And this might be not straightforward to see it, but what you can see actually is that this matrix here is also block diagonal. Now it's small and block diagonal. And it has exactly the same form. It has some small dense matrix, Kronecker product, a diagonal matrix, again small diagonal matrix. And this gives us two important properties. Just we have seen them on a two-dimensional example already, but to conclude, for the TT blocks corresponding to stochastic degrees of freedom, we have a direct solver because we have a small block diagonal matrix. Just use the Gaussian elimination, nothing more. And we have this reasonably small cost. Now with the constant here really of the order of 1. So it's really the constant from daily decomposition and a bit of other computations. So it's probably of the order of 5, no more. And if we store the degrees of freedom corresponding to our spatial discretization, we can store them in the first TT block. And this means that for the spatial degrees of freedom, this will again be a block diagonal matrix. And in particular, we will need to solve the number of deterministic PDEs which is linear in our rank. And our rank is supposedly small. So we can have it below 100 for a quite complicated case of a PDE, for a quite complicated model, and for very good accuracy, something like 10 to minus 5. So in this number here, it should supposedly be much smaller than the number of solves in the Monte Carlo, well, depending on the model. And that's what we want to look at in the experiments. But this is the most important points to take away. So if you look at the computations, so again, the problem which some people call the fruit fly is now equipped with some boundary conditions. And as my coefficient, I choose this so-called log normal expansion. So it's an exponential of an affine expansion. This affine expansion is produced by the Carhoonian law of series of the Mathyon covariance function for the coefficient with some parameters. So basically it has two parameters. The one parameter is this variance, which we can keep just one. And another is this nu. And what nu is basically, the nu tells us how smooth is our field, how rapidly do the norms of these terms here decay. So if nu is large, then this decay is very fast. And this basically means that we probably don't need all d dimensions. So for the latter dimensions, the terms there will be very small. And if nu is large, then our problem is effectively low dimension. If nu is small, then we have a very slowly decaying sequence here. And then we have essentially more random problem. So let's see what it does. Of course, we want to compare with some state-of-the-art techniques. So we use the quasi-Monte Carlo, which is a which is a deterministic method, in fact, but we can also do some shifts to introduce some randomness there. We can also implement it in a multi-level fashion using the hierarchy of spatial grids. And then we can use an adaptive sparse grid algorithm, and finally our hybrid algorithm in the Tensor Train decomposition. And as our quantity interest, I want to compute 10 moments of the solution, because what I want to do in the end, I'm not really interested in looking at these 10 moments, but what I want to do, I want to approximate my probability density function of the solution. And one way to do this is to use the maximum entropy methods on the vector of moments. And here is the motivation why I computed the whole solution in the first instance. Because if you want to approximate 10 different quantities of interest in the tensor representation, then the rank might be roughly on the same scale as the rank of the whole solution. And for the whole solution, we have this nice block diagonality of all reduced matrices. So you can just use this. And here is one example of this smoothness parameter. 4, it's reasonably high. I mean, in principle, to be honest, in this community, it's considered as very high. But what we can see here, if we plot the computational time versus the error, and this is the final error in my model, so it accounts for the tensor approximation error, the discretization error, and the Kahun-Lioff expansion truncation error. So everything in. We can see that our algorithm has the linear complexity. This is the optimal complexity, by the way, because, as I said, this error also accounts for the spatial discretization error, and this is basically the best complexity for the one deterministic PDE we can get. Then if we use the multi-level methods, then they also have the linear complexity, the linear slope, but the constant is now much higher, because now we need to solve roughly 1 over epsilon deterministic PDEs, and in this algorithm it can be much smaller. But if we use other single level methods like the single level quasi-Monte Carlo or the sparse interpolation, the slope gets much higher, because, well, here it's a bit unusual to have 3 here. Again, it's exactly because this error is quite a complicated object where we need to synchronize different refinement steps. Otherwise, it could be smaller, I guess, if we don't refine the spatial grid. But if you do refine the spatial grid and the dimension at the same time, then these slopes can get quite high, actually. And if you look at the number of deterministic solves, the difference is much more dramatic here. So there's really like a couple of orders of magnitude. If you get to the rougher field, then yes, the situation is more difficult. Here we see that the slope in the tensor algorithm is not 1 anymore. And yeah, so potentially it might even cross the multi-level QMC line at some point. But still, in terms of the number of solves, it's the difference is huge. And why it's interesting? Because in principle, the two-dimensional diffusion equation is not a very big deal. I mean, even if we use the sparse LU decomposition, it's very efficient. If you use multigrid, it's even more efficient. But if we had something like a 3-dimensional Navier-Stokes equation here, then the number of solves is really what would dominate our complexity. And then we would really be interested in this difference here. So just short messages to take away. So we can use some ideas from the linear algebra of Lorentz decomposition, like the alternating ration or cross interpolation, for solving high-dimensional differential equations, and in particular the high-dimensional stochastic PDEs. And there we can actually benefit from both the structure of the Lorentz decomposition and the sparsity structure of the matrix. Then, if the problem does have this Lorentz structure, if it has a fastly decaying expansion, for example, then these algorithms can be faster because they leverage this structure. If the problem is more random, then of course these algorithms can be less efficient. But then again, it's a single level method. And now it's very popular to do the multi-level, and it makes a lot of sense, because if we have a hierarchy of spatial discretization, it would be very interesting to use them. So now we have both the paper and the codes. You can read this. And of course, in real problems, we would not be interested in just solving the forward model, just solving the equation. But we would be interested in solving inverse problems. And it turns out that these Lorentz surrogates are actually some very efficient tool also for doing the inverse problem in a fast way. And I'd like to invite you to the talk given by Rob in the next mini-symposium, so who will speak about different aspects of the inverse problem, in particular about using low parametric surrogates for that task. But for me, that was all for today. Thank you.
Time for a few questions.
I have a comment, a general comment. You are discussing a discrete problem, and you fix it from the beginning.
Yeah.
And you say things about the complexity of solving that discrete problem. But the discrete problem is only a tool. You are really interested in the problem of the original continuous problem.
Yeah.
And if you fix a rank R, can you see from your computations whether what you get there is any good for the original problem? Really, the complexity should scale in the accuracy to the original problem, not to the accuracy of the discrete problem.
So that's exactly what we have here. Why it's fun? Because if we just consider the accuracy with respect to rank, or the complexity with respect to the accuracy when we only refine these ranks and not the other parameters of the model, then this plot here should actually be logarithmic, something like this.
But it should, but it's a guess. How can you ascertain the quantification of the accuracy you get?
So if you just want to ascertain the accuracy, you can apply a method on different sequences of parameters and compare them. Or you can...
How do you compare to the exact solution?
Well, you never have an exact solution.
What?
You never have an exact solution.
No, it's not true. We do have a posteriori bounds for the exact solution. And that gives a rigorous bound to the exact solution. In fact, provable in optimal time.
So you mean about estimating the complexity,
Yes.
not about guaranteeing that what you get is good.
You achieve a target accuracy for the exact solution, not for the discrete one. There is never a discrete solution. For the exact solution, and you can estimate the complexity of this process relative to the relevant benchmarks in such a case. That you can do.
I think you're talking about really proving the theoretical estimates of the ranks versus accuracy.
You insinuate that you are forced to do heuristic, which I say it's not true.
Yeah.
Okay, obviously that's a conversation you guys should continue to have. Do we have any other questions? No?
Yeah, actually, in this plot, so the number of solves versus different methods, that is summing up all the solves on all different discretization levels, right? At least for mine.
That's a very good question. So these methods are single level, so this is just one level. And here, different levels are scaled with respect to their relative CPU times. So if you measure the CPU times of one deterministic solve in each level, and then scale them to basically, so this is the number of solves at the finest level, effectively.
So why is it constant?
Well, because we exactly have this scaling. So if you just summed the number of solves from all levels, that would grow, of course, because the number of solves on the first level grows. But the number of solves at the finest level stays roughly constant.
Oh, but the level,
that's the idea of the multi-leveling.
But the level itself is increasing.
The level itself is increasing. Yeah, so here we have a slope of 1, and basically here is the CPU time over the error, because the slope for the deterministic problem is 1. So here it's 1 minus 1, 0. That's why it's constant.
Any final questions? Okay, no, thanks, speaker again.